In last class we have completed spherical mirrors. So, the reflection part is over. So, now we will be moving on to the refraction, that is what we will be starting off today. So, the topic is called refraction. So, this is another property of light which we will be studying about. So, to understand refraction, so we can consider a situation like this. Whenever let us say we have an interface of two different medium. So, by medium I mean two different types of material. So, for example, let us say this is air and this is water, or it could be any different types of material, a region which is made up of two different types of material. So, this region whole over here is made up of air and this region is basically water. And the boundary which we have between the two surfaces, two mediums, is what we call as an interface. So, this is called as an interface. Okay. So, first the idea here is that whenever light is incident from one medium and it strikes the interface of those two mediums, what happens is that at that interface two things can happen. One is that the light ray can get reflected back, some part of the light ray will get reflected back and some part of the light ray will enter into this medium. So, some part of light enters into the other medium. So, this is what generally occurs. So, whenever light strikes, even if you consider a glass slab here, and if light is incident on that glass slab, so even though it is a transparent substance, nothing can be 100% transparent, right. So, whenever light strikes that glass slab on one of its surfaces, so some part of the light ray will get reflected back, some part of that will enter into the next medium, clear. So, we have studied about what happens during reflection, what are the properties of reflection and all that. So, now we will be studying about what happens to this light which enters into the second medium. How does it enter? At what angle does it enter? So, that angle at which it enters, how is it related with the initial angle? So, that is what we will be studying in this particular chapter, and this property of light entering from one medium to other medium. So, that idea is what we will be learning about, and in this particular case we can say that when light enters from one medium into the other, the light bends at the interface, and this property of light is what we call as refraction. So, this property is called refraction. So, we have learnt earlier when we talked about properties of light in the initial lecture, we discussed that light undergoes this rectilinear propagation, which means that it travels in a straight line from one point to other point. I have told you one more thing there, that is valid in a homogeneous medium. If the medium is uniform throughout, in such a medium it travels in a straight line. But whenever it comes across an interface, a boundary between two different mediums in this particular manner, so near the boundary the light ray bends from its initial direction. If it was going initially in this direction, so after reaching the interface it might go in a different direction. Instead of going in the original direction, it might bend this way or it might bend this way. So, that is what we will be learning. So, that property is what we call as refraction, the property of light bending when it comes across an interface of two different mediums. So, that is the idea, and if you look for the reason why the light bends, so the reason is something like this. The reason is because of difference in the speed of light in the two mediums. Okay, or two media. So, that is the idea. So, the reason why light bends is because the velocity, the speed that light has in this medium and this medium will be different from each other. So, in air and in this case I have taken water. So, because the speed of light is different in the two mediums, and that is the reason why it bends when it comes across that interface. Now, how does speed, how can we relate that speed with the bending nature of light, right? So, let us try to understand that. So, this can be understood by something which we can call as Fermat's principle. So, I will explain this with an example, try to think about this scenario. So, let us consider a scenario like this where we have let us say this, here we have water, it is a lake, let us consider that this is a lake. So, whatever you have here which I am marking in blue is basically a lake, and here this region, let us say it is land. I am not talking about light here, I am talking about a person who is on land and who is a different person in a lake. Let us consider a scenario like that. So, let us say there is a person who is on land, he is standing at some distance from the lake, and there is another person who is in the lake. So, let us say he has fallen into the lake, let us consider that this fellow is the friend of this fellow, right, and he has suddenly fallen into the lake and he now has to go and save him, right. So, now think of this scenario, this person A is going to save this person B. Now, he is at some distance from the lake, and even after reaching the lake he has to swim some distance to reach person B. Now, A has different options. So, these are the different options which A has. So, first he can reach the lake and then swim this distance, right, or he can just go in a straight line from A to B, I mean from this initial position to this position, or he can go something like this and then go something like this. So, let us call these three paths as 1, 2, 3. Now, keeping in mind that you are this person A and you are going to save this person B, right, you are going to reach that person and save him. Now, keep in mind that your speed while running on land is definitely greater when compared to your speed at which you can swim in that lake. So, let us consider that. So, everyone will have their running speed greater than their swimming speed. I think I can safely consider this assumption, right. So, you can run faster than you can swim. Now, keeping that in mind, tell me which of these three paths will you be choosing. Now, keep in mind this is about the life of your friend. So, the faster you reach him, the easier, the more chances are there for you to save him. So, keeping that in mind, which of these three paths are you going to choose? Will you choose this first path where you run a small distance and swim a large distance, or 2 is basically an intermediate case. So, let us talk about 1 and 3. So, 1 is where you are running less and swimming more, and 3 is where you are running more and swimming less. So, which of these 3 are you more feasible to choose? Obviously, our common sense basically tells us that this is the more ideal scenario, and when you are put into such a situation without you knowing, you will definitely choose path 3, and that is what exactly light does. So, whenever light has to travel from one point to another point which are in two different media, light always chooses the path in which it can reach from those between those 2 points in the shortest time, and that is what we call as Fermat's principle. So, if I just say light is incident from here, if it has to reach B, if light chooses this path, then light will be able to reach that position in the minimum possible time. So, just like we have that common sense that we have to go from here to here in the minimum possible time, and we will be choosing a path something like this, light also does the same thing. Now, this has a slightly different explanation, a more mathematical way of approach also, which we will be learning in wave optics. So, for now just get this idea. So, the reason why light bends when it comes across an interface of two different media is because it tries to reach from here to here in the shortest possible time. So, when the speed changes, it will try to make sure that it travels larger distance with more velocity and lesser distance with less velocity. So, that is the basic idea. So, you can define Fermat's principle like this: light travels between 2 points in the minimum possible time. Right. So, that is the reason why light bends. If you consider a ray of light, so the ray of light bends when it comes across an interface. So, that is the basic idea. So, we will also learn about this mathematically. We will, just like we learnt about the laws of reflection earlier, similarly we also have laws of refraction. So, we will discuss about that also. So, to understand this, now that we have established that the bending of light has something to do with the speed of light in the two media, correct. So, wherever the speed is greater, the light tries to travel larger distance in that medium. So, it has something to do with the speed of light. So, wherever speed of light changes, light has the property of bending at that interface. So, let us try to establish a connection between the bending nature of light and the speed of light, clear. So, we will learn that in a while. So, the parameter which links the speed of light with the bending nature of light, so we call that as the refractive index. So, this is a very important term. Throughout the chapter we will be using this term continuously. So, proper understanding of this is definitely required. So, refractive index. So, it is denoted with mu. So, some cases it is denoted with mu, some cases it is denoted with n. So, refractive index. So, it is basically a dimensionless constant, it is just a number, and refractive index, it is defined for a medium. So, for a medium the refractive index is defined in this particular manner, C by V. Now, in this particular expression, so C denotes the speed of light in air or vacuum. So, which you all know as approximately equal to 3 into 10 power 8 meter per second, and this V represents speed of light in that medium. Which medium? The medium for which we are calculating the mu value, for which we are defining the mu value. So, that is how we define refractive index. So, speed of light in vacuum divided by speed of light in that particular medium. So, it basically means that if let us say there is a medium, so let us say this is some medium where if light is passing through this particular medium, so as light passes through this particular medium, let us say the speed of that light in this particular medium is 2 into 10 power 8 meter per second. So, if the velocity is that way, then we can define the refractive index of this medium as the speed of light in vacuum, which we know as 3 into 10 power 8 meter per second divided by speed of light in this medium, so which is 2 into 10 power 8 meter per second, and solving this will give me the value as 1.5. So, as you can see, it is just the ratio of two velocities, right, two speeds. So, whatever value which we get here will just be a number without any dimensions. It has no units, it is just a number. So, you can actually understand it like this. So, we can write a definition for refractive index. It is the number of times by which the speed of light decreases by when light enters into a medium. When light enters into a medium from air, or from vacuum. So, that is the basic idea. So, as you can see, if I consider this particular medium, so let us say this is medium and here we have air. So, as long as the light is travelling in air, the speed of it will be 3 into 10 power 8 meter per second. Now, the moment it enters into this particular medium, its speed is becoming 2 into 10 power 8. So, what we are finding out here is how many times is the speed of light decreasing by. So, when compared with this, can I say that this is 3 divided by 3 by 2? This one, if I divide this value by 3 by 2, I will be getting this value, which means the speed of light is decreasing by 1.5 times. So, that is the basic idea, that is how we define this. It is the number of times, or you can say number of times also basically mean the factor. It is the factor by which the speed of light decreases by when light enters into a medium from air. So, we are defining this refractive index with respect to air. So, when light enters from air into a particular medium, the speed of light reduces by how much factor, right. So, that factor, that number is what we call as refractive index. So, this is the basic expression which we have for that, and keep in mind it is just a number. And one very important thing which you will have to know here is that speed of light in any medium will always be lesser than the speed of light in vacuum. So, you know that, you must have heard of it also, speed of light will be the highest in vacuum and nothing can have, or no other situation can have a speed which is greater than the speed of light in vacuum. So, which means this V, the speed of light in a medium is always lesser than the speed of light in vacuum. So, which will automatically mean that the value of mu is always greater than or equal to 1. Equal to will be the case when we consider air. Clear? So, this is a very important result. So, mu of air can be considered to be 1. So, which basically means that we are taking air, the speed of light in air as the reference, right. So, if I define a parameter for air as 1, let us call that parameter as refractive index. So, for air I am taking it as a reference and I am defining that as 1. So, if air has 1, then what does other medium have? So, that parameter is what we call as refractive index. Clear? So, for air we are defining the value of refractive index as 1, which means we are taking it as reference, right. So, in air whatever is the speed of light, if I let us say associate 1 for that, then refractive index basically denotes the parameter which we are associating to other media by taking this as the reference, which means we are comparing with air all the time. In air, if the speed is some value, then in this medium the speed is 1.5 times lesser. Clear? So, that is how we understand the idea of refractive index. Now, in the same manner, just like we have understood here, there is also another type of refractive index which we will be talking about, which we call as relative refractive index. Relative refractive index. So, as I told you, when I just write mu, it means that we are comparing that with air, right, the speed of light in air. So, when I see a value of mu is equal to 2, it basically means that this medium has speed of light which is 2 times lesser than the speed of light in air. So, when I just see mu written, you should always understand that it is being compared with speed in air. Now, what does relative refractive index mean is that, so it is basically represented like this. Let us say I write it as mu 2 1. So, mu 2 1 basically means mu 2 by mu 1, right. It represents mu 2 by mu 1. So, this is basically called as refractive index of medium 2 with respect to medium 1. So, it means that this time we are not comparing it with air, we are not taking air as the reference, we are taking medium 1 as the reference. I hope you are getting this. In all the earlier cases, when I just write mu, so mu just means that it is absolute refractive index. Absolute refractive index basically means the factor by which it is lesser when compared with air, the speed is lesser when compared with air. Now, when I write a term like this, it means that I am comparing medium 2's speed with medium 1's speed, clear, and the value is given by mu 2 by mu 1, and you all know the expression which I write for mu 2. What is the general expression I write for mu 2? Mu 2 can be written as C by V 2 divided by mu 1 can be written as C by V 1, clear. So, when I simplify this, I will be getting this value as V 1 by V 2. So, which is what I told you just now. So, when I write mu 2 1, mu 2 1 gives me the number, and what is that number? It is the number by which the speed in medium 1 is greater when compared to the speed in medium 2, clear. So, mu 2 1, I will write it down once again here. Mu 2 1 basically means V 1 by V 2. So, this is basically a number which tells me the number of times the speed in 1 is greater when compared to the speed in 2 for light, clear. So, that is just a representation. So, most of the times we will be just using mu itself, clear, which means we will always be comparing it with air only. So, that is the idea. Okay. Now, let us see a situation where, let us take it as a question. They have given that the refractive index of water with respect to glass. So, water with respect to glass, which means refractive index of water by refractive index of glass. So, they have given that this value is 8 by 9. So, this is given to us, right, and they have also given us speed of light in glass. So, they have given that the speed of light in glass is, let us say, 2 into 10 power 8 meter per second. So, this is the information given to us. Now, using this information, we need to find out speed of light in water, and also let us say we also need to find refractive index of water and refractive index of glass. So, these are the values which we will have to calculate, right. So, now let us try to analyze the information based on the concept which we have seen. So, speed of light in glass is given to us. So, when I write the refractive index of glass, we know that refractive index of glass is nothing but C divided by speed of light in glass. So, when I substitute the value, what do I get? We know that the speed of light in air is nothing but 3 into 10 power 8 meter per second divided by speed of light in glass is given as 2 into 10 power 8 meter per second, correct. So, when I simplify this, I get 1.5. So, refractive index of glass is 1.5 or 3 by 2. Okay. Now, refractive index of water with respect to glass is known to us. So, using that we can easily calculate refractive index of water. You know the relation between mu g, mu w and mu wg, correct. So, you can easily complete that. So, I leave it to you. So, please do that. So, find the values of mu w and mu g I have already calculated. So, find mu w and speed of light in water. So, these are the values which we will have to calculate. Now, we know that when light enters into a different medium, its speed changes, right. Now, when speed changes, are there any other properties of light which will also change? So, let us see that. So, for example, let us consider that we have a medium to the right side, here it is air, let us say, and this is some medium. So, when light is incident in this way, so and as light enters into the next medium, so we definitely know that the speed changes because it is going from air into some medium. We can say that the speed decreases because speed of light is highest in air. Okay. Now, we also know that in the speed of light is generally written as f into lambda. You all know what this means. So, f basically represents the frequency of light and lambda represents the wavelength of light. So, when light enters from this air medium into some other medium, so speed is changing. Now, as speed is changing, these properties also should change, or at least one of them should change or both of them might change. So, what is that which changes when light travels from one medium to another medium? So, to understand this, we will first have to know what frequency means. I have told you earlier that light is generally produced by oscillating charges, correct. So, whenever the charged particles oscillate, they radiate energy. So, this frequency of light is something which is associated with the frequency of oscillations in the source, clear. It has nothing to do with which medium the light is traveling. So, whichever medium the light enters into, its frequency will always be the same. So, it does not change with change in medium. So, this is something which you will have to keep in mind. Frequency is dependent only on source. So, it has nothing to do with the medium in which the speed, the light travels. Now, you know that V, the term V is dependent on the medium. So, whichever medium the light travels, it can change with the medium. So, if you understand this, as light enters from this medium into this medium, so frequency is not going to change, right, because source is not changing, the same light is just entering into a different medium. So, f remains constant. Now, as a result of that, if V changes, lambda should automatically change. So, we can say that as light travels across an interface of two different media, its wavelength changes, but its frequency remains same. So, this is a concept which you will have to keep in mind. So, we will understand more about this concept when we discuss about waves, where we talk about the meaning of wavelength and what that means also. So, for now just keep in mind that as light travels from one medium to other medium, frequency does not change, only the wavelength changes, and the wavelength changes because the speed of light changes, and in this case we can say that the speed of light is directly proportional to lambda because frequency is constant. Now, using this principle here we can say that earlier we have talked about the relative refractive index. So, we defined relative refractive index like this: refractive index of 2 with respect to 1 means refractive index of 2 by refractive index of 1, and we have seen that this can be written as V1 by V2. Mu 2 by mu 1 is nothing but V1 by V2. It is inversely proportional to the velocity. So, if the speed of light in a medium is more, its refractive index is less, clear. So, that is the expression which we got, and because frequency will remain constant as light travels from one medium to other medium, we can say that V1 by V2 will also be equal to lambda 1 by lambda 2. So, this is the expression which we will be using, clear. And here if the medium 1 is air, then we can consider this mu value as the absolute refractive index, which is the basic term which we defined as mu. Otherwise, it is just called as relative refractive index. So, that is the basic idea. Now, let us talk about one more term which we will be quite frequently using throughout this chapter. So, it is called optically denser medium. So, whenever we use this term optically denser medium, so what that means? So, this is a term which we use to understand speed of light once again when I am comparing between two different mediums. So, this understand that this is something which is used in relative term. It is used in relative terms, which means only during comparison between two different mediums we will be calling one as optically denser and the other one as optically rarer. So, optically denser and optically rarer. So, these are basically relative terms both. So, when I have two different mediums, one of them might be optically denser and the other one might be optically rarer. Now, how do we define that? So, it is based on speed of light once again. So, a medium is said to be denser. A medium is considered to be relatively optically denser if the speed of light in it is lesser than in the other medium. So, that is a simple criteria. So, whenever I am comparing between two different mediums, the medium in which the speed of light is lesser is the one which is considered to be optically denser. Optically means for light, that medium is like a denser medium. So, that is the reason why light is moving slowly. So, the slower the light moves, more optically denser the medium would be, and you also know that the slower the light moves, higher will be the refractive index. So, we can easily relate the optically denser medium with the refractive index also. So, I can say that higher the refractive index, more will be the optical density. So, a denser medium among two different mediums, the one with more refractive index is also the one with more optical density or more denser medium we can say, and if one is denser medium, the other one will be rarer medium. So, keep in mind denser relates to slowness and rarer relates to fastness of light. So, wherever we have a denser medium, there the speed of light is lesser, and in a rarer medium the speed of light will be larger, clear, when compared with the other one. So, that is the basic thing. So, students, now that we have understood what refractive index is and what a denser and rarer medium is, so let us understand refraction and how it occurs. So, if I consider an interface of two different medium, so let us say this is a denser medium and this is a rarer medium. So, let us represent the refractive index of this as mu 1 and this one as mu 2. So, you know that if this is denser and this is rarer, which of these two will have the higher refractive index? The one with which is considered denser is the one with more refractive index, right. So, the situation which I am considering is where mu 1 is greater than mu 2. Now, if this is an interface of two different mediums, all the part above this is denser medium and below this is rarer medium, which means the speed of light in the first medium will be lesser when compared to the speed of light in the second medium. Okay. So, if I consider a scenario like this, and in this particular situation, so let us consider that this is the normal, right, and if light is incident, let us consider that light is incident at the interface of two different media in this particular direction. Let us call this angle of incidence as I. Now, we know that as light enters into the second medium I've told you earlier that some part of the light will get reflected also. Yes, some percentage of that energy of light will get reflected also, some very small percentage. Most of it will get transmitted or refracted into the second medium. So, now we are concerned about at what angle does it enter into the second medium. Okay. So, what generally was observed was, so what I am drawing now, this dotted line is the actual direction in which the light ray is incident. Okay. Now, as light enters from denser medium into rarer medium, it was observed that the light bends and travels in this direction. It bends away from the normal. So, this is the normal. So, whenever it enters from denser medium into rarer medium, the light bends away from the normal. So, this angle R is the angle of refraction. We call it as angle of refraction. Angle of refraction, and this is angle of incidence, just like we have defined earlier. Okay. So, that is the basic idea. So, this is an observation based result which I am telling you. So, whenever light is incident from denser medium into a rarer medium, as it enters into the rarer medium, the light bends away from the normal. So, it should actually go along the dotted line, but it is moving like this. At the interface, it is bending near the interface. The bending happens only at the interface, not after entering into the medium. So, at the interface it changes its direction, clear. So, that is a basic idea. So, I will write down what happens here. As light enters into a rarer medium, it bends away from normal. Right. Now, in the same manner we can say that if the light is entering from a rarer medium into a denser medium. So, let us say this is case 1, from denser into rarer. Now, similarly, let us see a different scenario where light enters from rarer medium into denser medium. So, let us call it as case 2. From rarer into denser. Right. So, once again if I consider the interface, mu 1, mu 2, this time this is the rarer medium, this is denser medium. So, in this case mu 1 is lesser than mu 2, right. Now, once again if I draw the normal and take an incident ray, so I is the angle of incidence. So, this is the direction in which the light ray was incident at the interface. So, now in this scenario what we observe is that the light ray bends towards the normal. So, instead of going along the straight line in which it was projected, so at the interface it just changes its direction towards the normal, it bends towards the normal. So, this would be the refracted ray, this is the incident ray, clear. And here the angle that it makes with the normal is the angle of refraction. So, that is the basic idea, and in this case we can say that as light enters into a denser medium, it bends towards the normal, clear. So, that is the scenario. Now, apart from this there are other observations also which were made. I'll just write them down here. So, for example, if there are two different media which have the same refractive index. So, let us say this is refractive index mu 1, this is refractive index mu 2, and if light was incident at the interface of two different media with the same refractive index. See, remember one thing, two medium can have the same refractive index even though the medium are different to us. For light, if the medium is allowing light to pass through in the same manner, then refractive index might be same. So, do not think that if mu 1 is equal to mu 2, they have to be same medium. So, they can be different media, but can have same refractive index also. So, in this case what was observed was that if the two media were having the same refractive index, the light just passes through. So, incident ray, refracted ray. So, in this case I is equal to R. So, if mu 1 is equal to mu 2, then I is equal to R. So, this was the observation which was made, and we can also write one more observation, which was if we have mu 1 and mu 2 as the two different media, and let us say this is the normal, and if light was incident along the normal only, which means normal incidence. So, if light is incident along the normal, so which means this angle here is 90 degrees, which means I is equal to 0. I have told you if this angle is 90, angle of incidence is not 90, right. Angle of incidence is measured with the normal. So, normal is also along the same line. So, angle of incidence will be 0. So, when angle of incidence was 0, the light just passed through without any bending. Clear? So, these are some cases which occur when light enters from one medium into other medium. So, in this case we can say that R is equal to 0. If I is equal to 0, R equal to 0. So, based on these cases we understand laws of refraction. So, how refraction occurs, we put that into mathematical form. So, we will be studying about something called as Snell's law, so which we will see in a while. So, let us now see the laws of refraction. So, the first law would be similar to what we have discussed in reflection. We can say that the incident ray, normal and refracted ray will lie in the same plane. Right. So, that is the first law. So, it basically means that, so we have already seen similar thing in reflection. So, this incident ray and this refracted ray. So, I have considered one particular scenario. You all know what this, when this case occurs, from rarer into denser, then it moves towards the normal. So, incident ray, refracted ray and the normal. So, all the three lines should lie in the same plane. So, in this particular scenario, all the three of them, all the three rays are in the plane of the board, right. So, that is the first law. Clear? Now, the second law, the most important one, is basically called Snell's law. So, some of you might have heard of this, might have used this. So, Snell's law. So, what it states is that, so when I consider different cases, let's understand that with an example. So, let's say we consider different cases like this. So, once again this law was proposed based on many observations and calculations which were made. So, let us say in all the three cases which I have taken, it can be many other cases also. So, in all these cases the upper medium has mu 1, lower medium has mu 2, and light was incident at the interface. So, let us say here the light is incident at an angle of I1 and the light ray refracted at an angle of R1, and now we change the angle of incidence, right. So, when the angle of incidence was changed from I1, a different angle. So, let us say I2, and even this case also once again the angle of refraction was observed as R2, right, and once again we change the angle of incidence and we observe the angle of refraction and so on. So, I3 and R3. So, once we found out different set of values of I1, R1, I2, R2, I3, R3 for a particular pair of two media, so mu1 and mu2 in all the cases. So, I am using the same medium, same interface, I am just changing the angle of incidence. So, what was basically observed was that, so by looking at the values of I1, R1, I2, R2 and so on, so it was observed that sin I by sin R was a constant in any case. In any case, whatever is the value which we got for sin I by sin R here was same as the value of sin I by sin R here and so on. So, whatever be the values of I and R you take, so this was always observed to be constant, and that constant was also observed to be equal to mu 2 by mu 1. So, I am taking a pair of media. So, mu 1 and mu 2 in all the cases. So, in such a scenario this term remains constant. So, this expression which I have written here is what we call as Snell's law. So, let us try to understand, let us try to see what this basically implies. Now, rearranging the terms in the same expression earlier, if I write that as sin I by sin R is equal to mu 2 by mu 1. So, rearranging this, cross multiplying these values, I will be getting mu 1 sin I is equal to mu 2 sin R. So, this is the general form in which we write Snell's law. So, you should understand it in this manner. The refractive index of a medium multiplied by the sine of angle that the light ray makes with the normal will remain constant. So, you can even consider multiple medium like this which are parallel to each other. So, multiple medium, let us say this is a medium of refractive index mu 1, a medium of refractive index mu 2, a medium of refractive index mu 3 and so on. You can call this as mu 4. So, in this particular scenario, if let us say light is incident on the first and second medium interface at some angle theta 1, and it enters into the second medium, let us say at an angle of theta 2, which is slightly different from theta 1. Now, as light which is entering from 2 to 3, if it undergoes refraction here, let us say it bends in this manner, and once again at this interface, let us say it bends like this. So, if this is how the light ray has travelled through the different interfaces which we have there, so we can actually write Snell's law at each and every interface by using this particular result which we have here, the refractive index of a medium multiplied by sine of angle that it makes with the normal should remain constant. So, which means that I can write mu 1 into sine of angle that the light ray makes with the normal is sine theta 1 is equal to, here I can write mu 2 into sine of angle with the normal, which is mu 2 into sine theta 2. So, that is the Snell's law equation I will write for this interface, this refraction. Similarly, if I write Snell's law for this refraction, what will I get? Once again, if this angle is theta 2, I can say this angle will also be theta 2, correct? Because these dotted lines, this dotted line and this dotted line are two parallel lines, and I am just having one straight line cutting those two. So, we can say that these two angles will be equal. So, this will also be theta 2, and if I call this angle here as theta 3, so I can write Snell's law for this interface also once again, which will give me mu 2 into sine of angle that the light ray makes with the normal, which is sine theta 2 is equal to, on the other side we have mu 3 and theta 3 with the normal. So, mu 3 into sine theta 3, correct. Similarly, for the last one, so once again I can say that this angle will be theta 3, this angle will be theta 4 and so on if it enters into a different medium. So, I can write mu 3 sine theta 3 is equal to mu 4 sine theta 4. So, that is the idea. So, whenever we have parallel interfaces, one interface parallel to the other interface in this manner, and a light is incident on one of the interface, we can say that if you see here, by using this I can say this value and this value are same, this value and this value are same. So, as the light passes through different media, we can always say that if the interfaces are parallel, the product of the refractive index and sine of angle that it makes with the normal should remain constant. So, in case of parallel interfaces, the value of mu into sin theta is constant. So, you can understand it that way, clear? So, that is the basic idea. Now, think of it like this, if this final medium which I have here, let us say the light ray has entered through different media, right, and if the final medium was once again mu 1, whatever medium from which it has started, if the final medium is also mu 1, can you tell me, can you understand what this final angle would be, right? What would it be? It would be theta 1 itself, because once again irrespective of whatever has happened in between, whatever is the product of mu and sin theta here should be same as the product of mu and sin theta even in the last medium, and if mu is same, then theta should also be same. So, that is the basic idea. So, if it enters into the same medium finally, it enters at the same angle once again, clear. So, I will maybe write that point down also. If the light ray enters into a medium of refractive index mu 1, right, it would enter at the same angle theta 1. So, whatever angle it had here theta 1, if it enters finally into the same medium, then it enters at the same angle theta 1. So, that is what we can say, right. Students, now we know that the light bends at the interface of two different media. Now, let us find out how much angle the light ray bends by. So, which we can call as deviation, right. So, if I consider a particular scenario where light is incident at an angle of I, and if it enters into the medium at an angle of R, so you can easily say that this was the initial direction of the light ray and it has deviated by this much angle and it is finally travelling in this direction. So, this angle by which it has deviated by is what we represent as delta, and you can see that in this scenario the value of delta is equal to I minus R. But in a general scenario, we are not sure if R is lesser than I or greater than I, because what I have written here is when light enters from rarer medium into denser medium. But if it is the other way around, then R will be greater, it moves away from normal. So, in that case R will be greater. So, let us put a modulus over here to find the magnitude of deviation, right. So, you can understand by looking at the case given to you whether the deviation is clockwise or anti-clockwise. Okay. So, the magnitude can be written as I minus R. So, that is the expression which we write for deviation. Okay. So, let us solve a question. So, let us consider a scenario here where we have two different medium. The refractive index of the first medium, or let us say the first medium is air, and the second medium has a refractive index of root 2, clear, 1.414. Okay, so now let us say light is incident at the interface at an angle of 45 degrees. We need to find out how much angle the light ray deviates by. So, find delta. Okay. So, first let us apply Snell's law and find out at what angle it enters into the second medium, right. So, we know that because this medium has a higher refractive index than air, which is having a refractive index of 1. So, it is entering into a denser medium. So, angle decreases, I mean the angle with the normal decreases, it bends towards the normal. Okay, so this is the direction in which the light ray travels finally, and I can find this angle, let us call it theta. I can find that angle by writing Snell's law. So, let us write that. So, I can say 1 into sine of 45. So, 1 into sine 45 is equal to root 2 into sine theta, root 2 into sine theta, correct. So, when I simplify this, sine 45 is 1 by root 2, another root 2 on this side will give me sine theta is equal to 1 by 2, which means theta is equal to 30 degrees, right. So, this angle here will be 30 degrees. Now, so if this is 30 and this is the initial direction in which the light ray was travelling, we can easily find delta. Delta is nothing but I minus r in this case. So, which is 45 degrees minus 30 degrees, which is equal to 15 degrees. So, that is the deviation in this scenario. Clear? We will solve one more question now. So, here it is given that a light ray was incident at some angle, and we know that whenever light is incident at an interface, some part of the light will get reflected, some part will get refracted, right. So, in this case the part of light which got reflected was like this. So, this is the reflected part, reflected ray, and the light ray which was refracted was like this. So, this is refracted ray, and it is given that it was observed to be in this way, that the reflected and refracted rays are moving perpendicular to each other. So, this angle between reflected and refracted rays are 90 degrees. So, let us consider this medium as air and this medium to have a refractive index of 4 by 3, right. 4 by 3 is generally for water. So, water has refractive index of 4 by 3 and glass has refractive index of 3 by 2. Okay, anyways, so let us understand this scenario. So, the angle between reflected ray and refracted ray is given to us 90 degrees. We need to find out the angle of incidence. So, I at which the light should be incident, so that this scenario can happen. So, this angle is I, which means we know that from laws of reflection this angle should also be I, and this is 90 degrees. So, which will automatically mean that this angle here should be how much? 180 minus 90 minus I, which is 90 minus I. So, this angle will be 90 minus I, correct. Now, you can directly apply Snell's law for this scenario. So, we know this is air and the angle here is I, this is water and angle is 90 minus I. So, if I apply Snell's law, I will get 1 into sine I is equal to, here mu is 4 by 3 into sine of 90 minus I. Sine of 90 minus I will be cos I. So, when I send this cos this side, it becomes tan. So, I will get tan I is equal to 4 by 3, and you know which value of I gives you 4 by 3, tan value. So, I is equal to 53 degrees. So, that is the angle of incidence in this scenario, right. So, we will see one more question now. So, in this case it is given like this, we have a medium like this which is spherical in shape, a spherical medium. You can consider it to be made up of a particular material which has a refractive index of root 3. So, root 3 is the refractive index of that medium. So, this whole thing is made up of a particular medium. Okay, so the outside surface is air, and let us say this is the normal where the light ray is incident. So, the light ray which is incident here is incident in this direction, making an angle of 60 degrees. So, that is given. So, now we need to trace that light ray. So, some part of the light enters, or we can say most of the light enters into the medium. So, once light enters into the medium, so refraction occurs and it goes and strikes the medium somewhere else on the other side, and refraction occurs there also. So, we need to find out the total deviation experienced by the light ray after 2 refractions, right. So, this is what we will have to calculate. So, this light ray will undergo refraction here, enter into that glass or whatever medium that is, that sphere, and it once again strikes the sphere somewhere, once again undergoes refraction and comes out into air medium, right. So, in this process we need to find the total deviation that it experiences. So, let us trace this light ray. So, because it is entering from a rarer medium, this is rarer and this is denser. So, we can consider this is the denser medium because of higher refractive index. So, as it enters into the denser medium, the light ray bends towards the normal. So, it bends like this. So, we need to find this angle first. So, to find that I will apply Snell's law, right. So, air, so the refractive index is 1 into the angle of incidence with the normal is sin 60, I will be writing sin 60 here, is equal to, here we have root 3 into, let us call this angle as r, sin r, right. So, that is the expression which we get, and we know the value of sin 60, root 3 by 2. So, root 3 and root 3 gets cancelled, and I will get the value of sin r is equal to 1 by 2, which means r is equal to 30 degrees. So, this light ray travels in this direction, making an angle of 30 degrees, and it goes and strikes the sphere somewhere over here. Now, there refraction can occur once again. The light ray can refract here and it enter into the air medium, right. So, if I draw a normal at this particular position, we know that normal drawn to a sphere should pass through the center. For a sphere, the normal should always pass through center. So, this is how the normal would be, and can you guess what the angle of incidence here would be? At what angle will the light ray strike that particular position? Now, you can see here this angle is 30 degrees, and if you look at the triangle which is formed inside the sphere, we know that this length and this length are the same, both are radius of the sphere. So, if this length and this length are same, the triangle which is formed is an isosceles triangle, and in an isosceles triangle these two angles should be equal. So, this will also be 30 degrees. So, I will just extend the normal further, and now we can say that the light ray just refracts, because it is entering into the rarer medium, it goes away from the normal, something like this. So, this is what happens to the light ray, right. So, let us call this as some theta. So, we need to find the value of theta. So, if you observe carefully, the light ray here is entering at an angle of 60, I mean it is incident at an angle of 60, enters into the medium at an angle of 30, and now here it is striking at an angle of 30. At what angle theta will it come out? You can easily guess that it would be 60 degrees. You can even write the equation. So, this is root 3, angle is 30. So, root 3 into sin 30 is equal to, the outside medium has a refractive index of 1, and the angle is theta. So, into sin theta. So, when you solve this, you will get sin theta is equal to root 3 by 2, which means theta is equal to 60 degrees. So, it comes out at an angle of 60 degrees. Okay, so light has this property called reversibility. So, reversibility basically means that if let us say light is incident at some angle, it undergoes multiple effects there like reflection, refraction, whatever, and let us say it comes out at some angle. What reversibility means is that if light ray is incident in the angle at which it has come out, then it just traces the path backwards and it comes out at the angle at which it was incident. So, this is the incident angle, this is the incident ray and this is the emerging ray. So, what we can say here is that if the light ray is incident in this manner, it travels like this and emerges out in this manner. In the exact same way, if the light ray was incident in the path of the emerging ray, it just traces the path once again and emerges in the direction of incident ray. So, this property of light is what we call as reversibility of light ray. So, I will write it down here, reversibility. So, keep that in mind. So, if I just change the direction of light in the emerging light ray, if I send light from in the path of the emerging ray, then light just once again traces back in the same direction and comes out from here. So, that is the idea. Okay, anyway, so we will calculate the deviation in this scenario. So, the light ray is bending twice in this case. So, first here, so light ray was initially travelling in this direction and it has deviated by this much angle. Let us call it delta 1, and you can clearly see from the diagram that the value of delta 1 is 60 minus 30. So, I can say that delta 1 is 30 degrees plus. Now, look at which sense it has deviated by, because I have told you deviation always should be understood with the sense as well. So, light ray was initially travelling in this direction and it has deviated towards this direction. So, the deviation is like this, which is clockwise sense. So, this is clockwise plus now the light ray is travelling like this. So, this is the direction of the light ray and now it has once again deviated by this much, right. So, you can once again calculate if this is 30, this angle will also be 30 and the total angle is 60, which means this angle by which it has deviated by will be 30 once again. Now, see which direction it has deviated by, like this, which is once again clockwise. So, I can say deviation is 30 degrees plus 30 degrees clockwise. So, the total deviation will be 60 degrees in the clockwise direction, right. So, that is the idea. So, keep this in mind, the idea of reversibility, we will be using it in some cases. So, it basically means that if the incident ray and the emerging ray which are coming out, if we interchange them, light still follows the same path. So, that is the basic idea. So, I will write it down, light follows the same path if incident ray is in the direction, in the opposite direction of emerging ray. Right. So, that is the basic idea. So, students, that is about the initial part of refraction. So, we have understood the basic ideas. So, Snell's law, the laws of refraction and how to apply them. So, the next class we will be discussing about the image formation when refraction occurs at a plane surface.